Welcome to week 2 of Advanced R. This week we're going to cover basic statistics and basic statistical plotting. So click on the week 2 link and here we are. We have a tutorial in basic statistics. And what we're going to do is we're actually going to cover a data set. It just holds some atmospheric and different weather variables in it, but it's called the Willow Creek data set. It's there's actually 3 different data sets for 3 different years in Willow Creek, Wisconsin, and these just hold different meteorological data and weather variables such as temperature and shortwave radiation, precipitation, pressure, humidity, etc. And we're going to talk about subsetting the data, talking about distributions, and just doing some basic statistical plotting here within R, and talk about some more advanced plots and then some correlation plots, and then we're going to use this data set for the assignment. But starting at the top, I have R opened over here, and really R was developed to be a statistical programming language. It wasn't until, R was initially developed in the 90s, and it really wasn't until 10, 15 years later people realized that, hey, this language has been built really on a really strong foundation that would lend itself easily to other applications beyond statistics. And now we have today's R, which can do just about anything you can imagine or want to do with a computer. And because the foundation was really in statistics, R has some very easy and easy to use functions. And so here are just some of the functions that can be useful, that can offer various statistical metrics or information. So we have length, sum, mean, median, standard deviation, min, max, and get into linear regression, summaries, normal distributions, probability distribution functions, and other distribution or fits. So, as I mentioned earlier, we're going to be practicing some of these functions via R, and the data set that we're going to use here is the Willow Creek weather data set. And so I'm going to copy this over and open that up. And this is what the data set looks like. This is a netcdf file. And for those of you who don't know, that's netcdf is one of the most popular data sets in sciences, really, and it's a very efficient binary format. It stands for Network Common Data File, data set format. And basically, what we're going to be doing here is extracting information from the raw netcdf file. So the first thing that we can just do this is a lot of cumbersome information, and it's all useful, but it's kind of ugly. It doesn't really do a great job. So let's break this down a little bit more. And let's come down here and let's print the names, the variable names that are stored within this netcdf file. So we have air temperature min, air pressure, eastward wind, so on and so forth, all the way down to precipitation. Now, the first thing that we're going to do here is we're going to load in each of these variables. So we have the netcdf file open, but we don't have the variables extracted from this data set. So we have queried the file. We have it stored as a netcdf file within R, but we need to extract the information and store these as matrices or arrays. So the way we're going to do that is we're going to first create a var names, which is just going to hold information for the actual names, what these variables are named as in the netcdf file. And we're going to create a list for all of our data to go in, and we're going to extract the dimension information. And so what we're going to do here is we're going to say for each of the variable names, grab the data using nc-var-get and put that variable into the Willow Creek 2010 list. And then we're going to convert that list to a data frame. Then after that data frame is created, we're going to change the variable names. Some of these variable names are really long, so we want to rename them. But first, let's just open the data, run this through the loop, and create it into a data frame. So Willow Creek DF. Here's what it's looking like, and it might be easier if we actually just open it with the view And so you see we have all of this data here, but it's rather ugly. So with that being the case, we are going to name the column names as the var names to start. So now, if we reopen Willow Creek DF, we have air temperature max, all of the variables that we read in. But still, some of these variable names are a little bit wonky. We still have surface downwelling long wave flux in air. It's just long wave radiation, just a very specific name for it. And we're going to want to rename that. So let's make a short names list here with just some shortened abbreviated names. Now, we're going to replace these names that we made up here with the short names. So let's go ahead and do that and then print out a head of the data set. Oops, short names wasn't defined yet. Cool, now we have tare, tmax, tmin, lwave, press, swave, so on and so forth. Now, this is a very key distinction, something that we need to expand upon here. This short names list right here must be in the same exact order as our previously named columns, var names. In other words, var names, the first element of the var names list must be air temperature, and the first element of the short names list must represent air temperature. So it has to be exact values and has to be in the exact same order, because all we're doing is we're just overwriting the names of these columns. So that's what we've done here, and now we have a data frame that has data for the 2010 Willow Creek data set for the air temperature. So this is a full year of data for these particular variables. The year is 2010. And as just another reminder, if you don't have the data downloaded yet, I highly recommend doing it like so, going over to the course GitHub, coming over here to code, downloading as a zip file, and that way you have every data set that we're going to use for this entire course. All right, so now what we need to do here is we need to add a date column. So we have all of these variables, but we just have a number of rows, and so we can actually print out length of the length of number of rows for any given variable is going to be 8,760. Now, we actually do know the units of time already. We know that this is an hourly data set. We have recorded air temperatures, pressures, precipitation values for each hour for this entire year 2010. But let's pretend we don't know that, and let's actually go through how you would go about creating a date time without knowing that from the start. So the first thing we're going to do is we have a time dimension right here. And we're going to print out the units of that time dimension. So, and remember, the reason that dim is designed and actually over here as an object is because we transferred the NC file dimensions, or the NC file dim, to a dim object. So now that's why we can use this down here. So the units are seconds, and let's take a look at how the seconds are spaced. So what we're going to do is we're going to go into instead of printing out the units now, we're going to dim time vals for values, and we're going to print out the first 10 values. And we can see that they're sequentially separated by values of 3600. So the unit is 3600, or the unit is seconds. It's spaced out by 3600 seconds. So 3600 seconds is 1 hour. So we have 60 seconds times 60 minutes in an hour, 3600. Now that we know exactly what's going on here, what we can do is we can create a date sequence here, and we can actually use the famous date function in R called POSIX CT. and we can create a sequence from January 1st, 2010 at 00 to December 31st at 2300 hours of 2010. And we can sequence this by hour because that is our separation between the values right there. So I'm going to come over here, create this date sequence, and we're going to add this date seek as a variable or a column in the Willow Creek DF data frame. And there you have it. So now we have, if we do a head on Willow Creek DF, we still have all of our weather variables up here, but now we also have a date time that shows each hour. So now we actually have a time series here for all the data. Because we have a time series, right now, we can actually go into trying to subset the data. Now, why would we want to do this? Let's say we only want to take a look at data from January 1st to June 30th. You don't need to work with the entire data set if you want to do that. So let's make a new data set called Jan to June. And the way we're going to use this data set is we're going to use an indexing form. We're going to index the data. We're going to find which indices they lie at. And then we're going to separate the data, the rows, by that, because we know that our rows are time index and the columns are the specific weather variable for that specific index. So we're going to copy all of this over. And now first we're going to start the start in. So we're going to say, okay, which date time give me the indice for the date time that's equal to January 1st, 2010. So that should just be 1, right? Because the data set starts on January 1st, 2010. Now we want to print out June 30th. And so we're going to say, okay, give me the value of the date time variable when it is equal to June 30th, 2010. And we have 4320. So these are our indices right here. So now I can grab this data frame and I can subset it using these indices. So we have a start indice and an end indice. So we can say my start ind is 1, my end indice is 4320. So I want rows 1 to 4320, column blank. When we have column blank, that means we want all. So we want all columns for these rows. Now, if I do a summary on Jan to June, date time, my max date time is 6:30, and my min date time is January 1st. So now we have this nice subsetted data set. And what we can do now is we can actually plot some different trends and distributions from our subsetted data set right here. So the first thing I'm going to do is I'm going to plot just the time series of the air temperature against the date time variables. And as we suspect, in the northern hemisphere, temperature increases from January all the way until all the way through the summer. So we have an increasing temperature right here. That'll make sense. And what we can actually do is we can actually fit a trend line or a regression line to that using the LM function. So LM stands for linear model. LM is used to fit linear models. And so we can describe, we said, okay, I want you to fit a linear model to tear and date time of the Jan to June data set. Run that line of code, print out the fit. So this is our formula right here. So we have our intercept and our x, and we can print out a summary of the fit, and it'll actually give you a little bit more information. It will give you different residuals. So this is difference from the regression from the mean is a residual, and we have different coefficients. So we have estimate, standard error, t-value, so on and so forth. So we can actually run the coefficients. Coefficients, again, there's the intercept, there's my x value. And now we can use those plotting skills that we learned last week to turn this time series into a time series with a regression line and a legend. So we plotted this up the same way, right? Plot it up, we add some information about some Y labels, some Y labels and some X labels. We gave it a main title. And then we can add a grid. Add a grid to that every 10 values. Then we can add in an ab line. And remember earlier, last week, what we did was we added a vertical line just to show that it was possible. But it is also possible to add in, to say, hey, use ab line to throw the fit on there. So it's using the coefficients from the fit, so that is the intercept and the X value, to add that trend line. And then finally, we can just add a linear regression, or we can just add a legend here that just shows that this is what that is. It's just a linear regression line of fit. So that shows us a lot of information. It just shows us the general trend. We're increasing, makes sense. And now what we can do is we can make a histogram of this specific data set. So let's go ahead and let's do that. And just a rule of thumb, it's a very good idea to actually annotate your code. I'm just running through this to show that it works and to kind of describe it, but I'm not going into great detail. But in your case, if you're saving this code, it might be a good idea to do that. Anyway, this is our histogram of Jan to June air temperature. And so we see that it follows a pretty normal distribution, but we definitely have the highest density of values between 285 and 290 Kelvin. So that kind of makes sense. But now let's create our own temperature bins, right? So this is just default bins. So we have they're binned every 5. So every 5 units of temperature, in this case it's Kelvin, it is automatically binning. So that's how the histogram function works. Now we're going to add in our own temperature bins. And then what we're going to do is we're going to calculate d norm of this, right? And so if you have a question about d norm, it's just a normal distribution. And we describe it up here in this little dictionary as well, just so you can kind of get a feel for it. But the reason that we're calculating this is because we want to add a line of normal distribution for our 100 bins, our temp bins. So here's our X, there's our mean, there's our standard deviation. And so we want to say, okay, given that information, create a normal distribution. So that's what Y is. And now we can just add lines of Y to that. So Y is the normal distribution. Here's what Y looks like. Just values of density for a normal distribution given this mean, this standard deviation, and these bins. And then we can just add lines to the plot. And here's our normal distribution. So it fits a normal distribution fairly well. We can see that we are represented here under the most likely temperature, and we're kind of overrepresented just here at the edges right here. But this gives you a really good idea of just how to display a histogram and a normal distribution, or a nonlinear distribution you could actually add to as well. There's all kinds of different distributions that you can add to a specific plot. So that's a histogram. Another way to show the same type of image is a density plot. And the way we're going to do that is we're going to calculate the density of the air temperature with a bin width of 0.5. So now our bin width up here was 5 for this histogram. Now we want the bin width to be 0.5, so 0.5 degrees. So what this is going to do is it's going to create a little bit of a more jagged density plot. And then what we can do, after we calculate the density there, you can just plot it up. And so this is our density line right here. So these are both showing the same thing. You know, we have a concentration of the most likely temperature for this year, or sorry, from this time frame of this specific data set is going to be somewhere between 285 and 290. And if we take a look at the density with a little bit of a tighter bin width, we see that actually that's mostly concentrated up here about 289. So that's the most likely temperature, has the highest density, has the highest amount of recurring times that value is displayed. Then we can use this fancy polygon function to say, hey, I'm going to color in this polygon D, and we're going to color it with the coral color, and we're going to give it a blue border. So just a very easy way to make a colorful image to show the density of air temperatures. Now, sometimes, as I mentioned earlier, we knew that this would follow a normal distribution because, for the most part, that's what temperature does. It follows a very normal distribution. Sometimes that's not always the case, but we don't always need to try and test out each one and take a look at the image and look at it ourselves. There's actually a package called FitDistR+, which will find the best fit for a particular data set. So it tests out normal distribution, gamma distribution, all these different statistical distributions for us, so we don't have to. So what I can do over here, let's make sure I have the package. Okay, cool, I have it. It loaded successfully. A reminder that if you don't have it, just install it. Like this, install.packages, FitDistR+, and I'm not going to execute this line of code, but if you needed to, you could. So we're going to load that up, and now what we're going to do is we're going to use the plotDist function, and look at this, what it automatically does for us here. So it automatically shows an empirical density and the cumulative distribution of data. So here's our CDF, and this is our empirical density. This is not a normal distribution. This is just the empirical distribution, what it looks like. Now what we can do here is, again, we know that a normal distribution is best, but let's actually go ahead and use DecisionDist, which will tell us, it'll plot for our air temperature data set all of these different distributions. And basically what we're looking for is which theoretical distribution is closest to our observation. So we actually see that a uniform distribution is actually better. It is a little bit closer to our observation. Normal is not that far apart though. We see that the uniform, the triangle right here, is closer to our observation than the normal distribution. And then further away is logistic, is pretty far away. It wouldn't do a very good job. But we also see that normal is fairly close to the line that would be a gamma distribution or log normal. But we also see that way down here, exponential does a very poor job. It is not an exponential distribution. But again, this simple function from this package, DESC this is decision of distribution, can very easily plot this Cullen and Frey graph, which will show you which distribution is best for that data set. We can also print out some summary statistics for that. That's what happens when you run that, which is nice. And then so we see that uniform, normal, and gamma are our closest distribution. So now what we can do is we can plot all three of these. So what we're going to do is we're going to run our FitDist. We're going to fit the distribution of air temperature to uniform, normal, and gamma. So, oops. If I actually just print FitG out, it actually has an estimate, a standard error, a shape, and a rate, everything that it goes into a gamma distribution. And I can also just print a summary on that, which will just give me a little bit more information. And so that's just going to give me a log likelihood, the correlation matrix, some useful different parameters. And now what I can do is I can create a plot that shows off these just different distributions. So what I'm going to do is I'm going to create a 2x2 plot using my mfro and my graphical parameter functions. And I'm going to plot a density plot, a CDF plot, a QQ plot, and a PP plot. And what these are going to show is theoretical densities over the data set that we've already calculated. So here we go. We can see that there's not really a whole lot of difference here between uniform, normal, and gamma across the data set. And obviously uniform, although it's closest, this does not do a poor job. And remember, this is part of statistics, right? So uniform right here is just a flat line. There's nothing to a uniform distribution. It's just saying that for all else it's equal. We have a mean temperature. And basically this is just showing that for this data set, which we slimmed down, we only have January to June, uniform does a decent job. But that being said, it's not nearly as visually pleasing as normal or gamma. If we actually use the entire year, uniform would not do as well. So then if we actually crunch the cumulative distribution functions, this is what it's looking like. So again, you have uniform, just a straight line every day, every hour of temperature is the same. We have a normal distribution that it's normally spread out, and it fits the actual empirical line, which is black, much better. Then we have our QQ plot and our PP plot, and these are just different statistical plots that will show different distributions. And basically what we see is that gamma and normal distribution fit the empirical data best for each of these two plots. And so this is probability. It's a empirical probability versus theoretical probability plot. That's what the PP plot is. And QQ is empirical quantiles versus theoretical quantiles. Now, I'm not a statistician, but you can use R and to do statistics for you, and everything's kind of a black box, and that's okay, because not everybody who's going to use R is going to be a statistician, but some of these metrics are still rather useful. So the last type of plot that we're going to cover here today is correlation plots. And so for each example before this, we've only been dealing with air temperature, but let's say that we were interested to know the correlation between air temperature and precipitation, or wind speed and pressure, and so on and so forth. So what we want to do here is we want to install the CorePlot package. So if you don't have it installed already, you're going to want to install it, and just loaded mine up. And the first thing that we need to do is we need to actually delete. We're going to make a new data frame here called Willow Creek no date, and we're going to null out the date time because it will create problems for it, because we need only numeric values. We can't have a specific date time. It can only be numeric. Another way around this would be actually create different hours of, you could create different variables with an hour of the day or a day of the year, but you can't feed it a date time of something of a variable, the date time class. We're just going to get rid of it for now, and we're going to calculate the correlations between all the variables. So here we go. See that here's our correlations right here. So we see that air temperature is very highly correlated with specific humidity. Air max and air min are very highly correlated with this as well. Not surprising. Temperature max is highly correlated with TARE. Not surprising at all. And now what we can do is we can actually calculate the residuals of a 95% confidence level. So again, this is just difference from the mean at the 95th confidence level. So we're giving ourselves a 5% error. to work with here. And then we're going to use the core plot function. And we're going to give ourselves a matrix of residual values. We're going to color it all up. We're going to adjust the magnification. We're going to add the color of the coefficients. We're going to add significance to it as well. And ultimately, it's just a visual representation. And actually what I'm going to do so this shows up better is I'm going to use mfro to reset my graphical settings 1:1, so we just fill up the full window here. And now we're colored here. So the darker the blue, the higher the correlation, the darker the red, the lower the correlation. So this is kind of a nice visual representation of what's correlated with what. And yes, we have, for example, air temperature is highly correlated with long wave. Air temperature, as we mentioned before, is highly correlated with specific humidity, and so on and so forth. So it just combines a rather easy way to just show correlations across variables. So for the assignment, I'm going to ask you to work with the 2012 year of the Willow Creek dataset instead of the 2010. And what I'd like you to do is to work with that data set to accomplish these questions right here and accomplish this assignment. And then what I would like you to do is append these figures to a document and answer the question. So the first being subset the data between July 1st and December 31st. I'd like you to create a scatter plot with a trend line of shortwave radiation. So very similar to this plot right here, but instead of for air temperature, I'm going to ask you to use S-wave is what we named it for our short names. So S-wave right here. And so I'd like you to make a plot like this, but for the shortwave variable. Does the trend line make sense? Why or why not? I'd like you to create a filled density plot of shortwave radiation similar to the air temperature one above. And yeah, so very similar to this plot right here. Does it make sense? How are these two different? And then last, create a correlation plot of Willow Creek 2012 and talk about how it compares to the 2010 dataset that we used above. So you're going to create a plot for 2, 3, and 4, and please attach them to a document with the answered questions and submit the document to Canvas. There is an extra credit opportunity if you'd like. It's not mandatory by any means, but using these 3 data sets, fuse them together into one continuous data frame, resample the data from an hourly to a daily resolution, plot air temperature for your new combined data frame, and add a trend line to it, and submit this new extra credit assignment labeled extra credit PNG. So I only care about the image, I don't care about the code, but yeah, if you can do that, you will get extra credit.